Hello, I am Nicolás Avalos. I am a PhD student at the Instituto Balseiro in Bariloche, and today I will talk about the Dark Matter Daily Modulation experiment, or DMSQUARE as we like to abbreviate it. This is an experiment in which we look for a diurnal modulation of potential dark matter events. We are carried in Bariloche, and we are using a Skipper CCD as a detector. So why would this day modulation happen? Well, we know that the solar system is traveling around the center of the galaxy and that there is a dark matter halo in the galaxy. Now, we see this halo as a dark matter wind that is coming towards us from the direction of Cygnus constellation. Now, this dark matter wind would come from 40 degrees north, and we are here in Bariloche at 41 degrees south. This means that at a certain point of the day, the constellation of Cygnus will be barely above the horizon, and the dark matter particles that come from this wind should only get across the atmosphere to reach our detector. However, 12 hours later, these same dark matter particles will have to cross the whole interior of the Earth to reach the detector. And the main point is that if the dark matter particles interact with the nuclei or electrons that conform the Earth, then they may scatter away or lose energy before reaching the detector at this point. And this will translate into a different rate of events in our detector between this first point and the other. Now, this is a sidereal day modulation, and it's different from a solar day. Therefore, if at some point of the year we have a maximum rate or flux of dark matter particles during the midnight, then 6 months later, we should have this maximum flux, but at midday. And then we can rule out potential solar day modulations, for example, because of temperature. Now, I will talk about the detector. We use a Skipper CCD, but first I will talk about scientific charge-coupled devices, or CCDs. They consist of a silicon bulk. On their surface, there is an array of pixels. Any incident particle that deposits energy in the silicon bulk generates electron-hole pairs, and then these holes drift towards the surface of the CCD where the pixel array is and get trapped in a potential well. Now we can move the charges that are trapped from one pixel to the next, first vertically and finally horizontally towards the sensing node. And this acts as a capacitor that allows us to translate the charge into voltage. And then this voltage is converted to a digital value, and we can generate an image. In this case, we use the CCD as a particle detector, and we see that different particles leave different traces in the CCD. Now, these regular scientific CCDs can achieve a readout noise of around 2 electrons, and this allows for a low energy threshold of around 50 electron volts. But we would like to have an even lower energy threshold. And this, after many years of research, was accomplished by making a change in the sense node. And now we can read the charge of the same pixel a lot of times, therefore reducing the total readout noise by the square root of the times that we read this charge. For example, if we read the charge 100 times, then the noise would be reduced by 10 times. And this allows us to read an arbitrary number of times and reduce the detection threshold down to the silicon band gap. And that is to say, around 1.2 electron volts. So now we can detect single electron in the pixels. I will talk now about the DMSQUARE experiment itself. This is the actual detector that we use. It is a prototype Skipper CCD of less than 100 milligrams of detection mass. This is the active region of 1 × 2 centimeters of surface. We have 1 megapixel, and they are 200 micrometers thick. And we have 4 readout amplifiers, 1 on each corner of the CCD, that allow us to reach each quarter of the CCD in parallel, and therefore reduce the total readout time. All of this is inside this copper packaging and inside a vacuum chamber. But why do we need this vacuum chamber? Well, because the CCD needs to be at a cold temperature in order to work properly. So we have a liquid nitrogen tank and a cold finger that acts as a thermal coupling between the liquid nitrogen and our detector. And now we can have our detector at a temperature of around 100 Kelvin. Now, in order to obtain data from our detector, we first have to do some pre-processing. We have to average these Skipper samples. We have to subtract a baseline, and for that we use the overscan, that is a region of the image which pixels have not been exposed, and therefore we know where the 0 is. We need to remove the crosstalk, which is a fake signal in 3 of the amplifiers when the other amplifier has a positive real signal. We should calibrate the image, and we fit these Gaussians here in this histogram, and the mean of this Gaussian minus the mean of this Gaussian is the gain of each amplifier. Then we divide the value of the pixel by the gain, and we obtain a total charge of the pixel in electrons. But in order to reduce even more the noise, we can subtract noise that is correlated. In our case, the 4 amplifiers fluctuate the same, so we have developed a method to separate the populations. I have no time to get into further detail, but if you want to ask anything, please do so during the discussion panel. So now we have an image in which we can distinguish the pixels which have 0 electrons from the ones who that have 1 electron, 2 electrons, and so on. What we need is to count the number of pixels that have only 1 electron. And also we need to save the date and the time of the readout and the total readout time. And with this data, we can compute the incidence angle of the dark matter wind, execute a simulation, see what is the expected rate for a certain dark matter model, and then compare it with the actual data. This is exactly what I will show now. So we have in green here the observed events per image. In blue is a simulation of how many single electron events we should have in our detectors. And in gray, it is the mean of these dark matter events. So in this case, for 1 MeV of wind mass and 5 × 10⁻27 scattering cross-section with electrons, we see that we should have a lot more events than what we see. Even if we averaged the total number of events, we can recheck the model with the data of our detector. However, if we lower a bit the scattering cross-section, we now cannot recheck this model by direct observation. However, if we look at the modulation that we should have, then we can say that this model is rejected by the data. And finally, if we reduce even more the cross-section, we will reach a point at which we cannot reject anymore the model, and that will be the limit that we will report. So the important thing here is that the search for the modulation allows us to set stronger limits to the cross-section, even if we can't reduce the background. We have background, but this background is not modulated. So if we compare it to the modulation, then we can reject better models. So we have been taking data since August of last year. That is almost an year of interrupted runs. In order to read the whole Skipper CCD, we apply a 1×5 hardware binning. So each of the image takes 1 hour and 15 minutes to be read. So that is the exposure time. And this corresponds to around 5 milligrams a day per image of exposure. We have an issue with data stability. Every run, we have a different background and different fluctuations in the 1 electron event rate. So we apply a Gaussianity test to the data. If the data pass this test, then we can include them in the analysis. And after this quality cut, we remain with 2,500 images, summing up to around 3 grams a day of total exposure. So these are the limits that we can set with our experiment right now. In orange, we can see the limits set by looking at the direct observation of the data. And in blue, we can see the limits set by looking for the modulation. As we can see, the orange limits is very similar to the protosensei at surface of 1 electron. They also looked at 2, 3 electrons, so they set more stringent limits to higher masses. But in the region of 1 MeV, well, it's very similar because they had a very similar detector. However, when we look at the modulation limits, we see that we can rule out about 1.5 order of magnitude more because we search for the modulation. So it is very important to say that with this prototype detector and at surface, well, we have very interesting limits. Now, we would like to improve these rejection limits. And there are 2 options for this, at least. The first one is to increase the exposure. As I said before, because we are searching for a modulation, if we increase the exposure by n times, then the error bars will be reduced by the square root of n. Therefore, we can install more or bigger CCDs. But the other option is to reduce the fluctuations of the 1 electron events. We have a lot of background, and some sources of this background, we know where it comes from. For example, we have charge generation when we turn on the acquisition board. We have light emission in one of the amplifiers. We have serial register events, which are very annoying. We have charge transfer inefficiencies, especially in columns. We also have thermal noise because the CCD cannot be at 0 temperature, and a spurious charge produced when we move the charge from 1 pixel to the next. But the dominant background right now is the fluorescence or Cherenkov radiation, or simply charges that spread from cosmic ray events. And this leads me to the last part, which is the future of DMSQUARE. We are going to go underground. We will move the experiment to Sierra Grande. In that place, there was a similar search carried during the 90s, which used germanium detectors. So they had a threshold much higher than ours. In this place, there is an inactive iron mine, which has horizontal access to around 400 meters underground. And therefore, if we install the experiment there, we will be shielded from external cosmic rays. So we look forward to going there. We plan to go by the end of October this year, and therefore see if we can set even better limits. So to sum up now, with a 100 milligram prototype detector that is operating on surface, we are able to improve the current surface limits to dark matter electron interactions. We are planning to move the detector to an underground site by October, and similar experiments can benefit from the search of the modulation, as long as they have the required time resolution. So thank you very much for hearing, and if you have any questions, please feel free to ask them during the discussion panels. Bye.